So let's just pick up right where we left off, and we're going to move on to talking about arguably the most popular of the post-quantum tools, which is lattices. And I can't possibly give lattices any justice here. My purpose is just to like very loosely say what they are, how you use them for crypto, and why they might be quantum resistant. Okay, so a lattice is just this regular grid of points in the plane, or we should actually imagine in very high dimension, something in the hundreds, but I can only draw a plane. Okay, and these points go off to infinity. So there's these things called bases, where the basis is basically a linearly independent set of vectors, such that integer combinations of those vectors generate the whole lattice. And we can have different types of bases. So here's one that looks very nice, and I hope this is a basis if I did it right. The red ones are a different basis. And what are the hard problems that we care about on lattices? Well, so one is the shortest vector problem, or for crypto, we really care about an approximate version, which is given a lattice. So you can describe, even though a lattice is an infinite object, you can describe it succinctly by a basis. So if I give you a basis for a lattice, your goal is to find the shortest vector or something that's not too long in the approximate case. So I believe this is the shortest vector in that lattice. And then the other problem, and shoot, there's a typo, that should be CVP, is the closest vector problem. And here you're given a point, and your goal is to find the closest lattice point, or at least a lattice point that is somewhat close. That's CVP. Okay, so these are the two hard problems in lattices that we care about. So an interesting thing with lattices is that different trapdoors allow you to do different things. Different bases allow you to do different things. So one thing you can do is you can give out this really long basis with long elements, PK, as your public key, and then you can keep a short basis as your secret key. And it turns out that this allows you to do effectively a trapdoor. And the very, very rough intuition, but basically if you have a basis, a short basis allows you to solve approximate closest vector, and the algorithm is kind of what you would expect. So you write this lattice point as an integer combination of your basis vectors, which you can do just by the definition of it being you don't have the lattice point. Your target point, you're trying to find a close lattice point. You write it as a linear combination over your basis vectors, and it won't be integer coefficients because the point's not on the lattice. But hey, you just round the coefficients, and if you have a good basis, it'll give you some goodness, some good approximation to the closest lattice point. And the point is that, yeah, the shorter the basis you give, the better rounding you can get, and the closer lattice point you get. And this gives a way to encrypt. Now, normally when we use lattices as an encryption scheme, we don't write it like this. We write it, kind of like matrix vector product notation and talk about learning with errors. But I'm just kind of keeping it to the underlying lattice structure here. So how do you encrypt a message M? Very, very roughly. You somehow map M to a lattice point. I'm not going to tell you how, or I'm going to be very vague about that. And then you move it a little bit off the lattice, and that point off the lattice is going to be your ciphertext. And intuition for security is that, well, closest vector is presumably hard, given you're given this bad basis in your public key. So actually computing the message, that's solving closest vector. That's supposed to be hard. But you have this cheat. You have this secret short basis, and by rounding, that allows you to actually do the decryption. Okay, that's just like a very, very high-level overview of what lattices are and why they can be used for crypto. There's obviously been a whole ton of literature on doing a lot of interesting crypto from lattices, which I just can't get into today. So the short answer solution problem and learning with errors problem that you may have heard of, these are just they're specific average case instances of SVP and CVP that have nice properties because they're, there's worst case to average case reductions and stuff like that. Okay, so what's relevant for us is why should these be post-quantum? And the first thing to notice is that lattices are periodic. They're like, by definition, they're kind of a periodic structure. So that should maybe set off alarm bells, like, okay, why am I thinking these as post-quantum when there's like all this periodicity to lattices? But I guess the point is that the lattice period, the lattice is a period, but it's known. You're usually given a short basis for the lattice. The hard problem is not actually finding the period, because everyone knows it. The hard problem is basically finding like a small, in Euclidean norm, a small representation of the period, or like a short vector you can think of as that doesn't completely describe the lattice, but generalization would be finding a short basis. That's like finding a short representation of the period, and that's just a fundamentally different problem than finding the period itself. And again, you're given the period, so we don't even care about the hardness of finding the period. Yeah, so period finding just doesn't seem relevant at all to lattices, and for that reason, and people have also tried other approaches to breaking lattices, but so for those reasons, we have presumed quantum hardness. But as with everything, it's always going to be a conjecture. Yeah, and I just want to point out that I am just focusing on quantum here, and why this is a good candidate. There's tons of reasons to study lattices beyond quantum. I won't get into those. Okay. Yeah, and that's about it for the concrete post-quantum assumptions I want to talk about. There are a bunch of others. There's assumptions from coding theory. There's learning parity with noise. There's crypto systems based on non-abelian groups. This is kind of a different way to constrain the structure of Diffie-Hellman while avoiding Shor's algorithm. And as I said before, most of symmetric crypto seems safe. And then you can also make generic assumptions. Usually you'd want to instantiate these generic assumptions from some concrete assumptions, but just for the purposes of, doing crypto, you can make the assumption post-quantum PKE, post-quantum PRGs, etc. Okay, I think there's a lot of open questions in this space. I think the main one is we just need a better understanding of the quantum hardness of these objects. People have tried, and especially lattices now have had a couple decades of people looking at them, but we don't have the same number of eyeballs on these problems as we've had for the classical crypto systems, nor the same amount of time. So our confidence in these things is much less than classical crypto. Another thing that I'm particularly interested in is finding more techniques for using group actions or showing barriers to it. So again, we had all this nice intuition from the classical group setting, and we wanted to try to port that over to the quantum setting using group actions, but things break down, and so we need more techniques to kind of replace those broken techniques. And I think an especially fascinating question is exploring what you can do with non-abelian group actions, and are there limits to what you can do? Can you get public key encryption from a generic non-abelian group action? And then maybe this is more of a practice-related question, but I think there's some interesting theory here. But understanding the exact security of symmetric crypto, I think, is very important. So are there non-trivial algorithms for SHA or AES? There are, but I don't think any have gotten to the point where they're actually like saying, oh, well, hey, you can be.
What's known besides the
I mean, basically nothing, but I'm not really familiar with this literature, but there have been some works, just like in the classical world, you look at round reduced versions or kind of simplified versions and you show attacks on them. There have been some efforts along those lines to analyze these against quantum attacks. I don't know that there's been really anything major though. And here I'll just advertise a question that I think is really interesting, which is, okay, so we have a really good idea of the hardness of inversion. So there's this Grover's algorithm that has a quadratic speedup over brute force search. We also know that's optimal generically. And we have collision finding. Classically, it's 2 to the n over 2 because of the birthday bound. Quantumly, it goes to 2 to the n over 3. We also know that that is the right value. However, this only looks at time. And actually, these ignore space. So in the classical world, the collision algorithm you can actually get in constant space. Quantumly, you can invert in constant space. But this collision finding algorithm actually requires 2 to the n over 3 space as well. And I think it's just a very interesting, I mean, it's basically a query complexity question, but it has importance for understanding the quantum hardness of symmetric crypto. Is 2 to the n over 3 time and space actually necessary, or can we get the space down constant, or what's the right trade-off there? Okay, so with that, I want to move on to the next part, which is talking about security proofs. Okay, so we have our foundation now. We'll assume that we have nice secure crypto, and now we want to use it to build other things.
Question.
Yeah.
So in those things that you showed, the candidates on the NIST, I guess, standards that you showed, they require CCA security, right, or something like that. So they use hashing in the middle.
Yeah, to get CCA security, they basically do some Fujisaki.
Right. So, but then if you apply Grover to that, what does that mean?
Yeah. Okay. So for CCA security specifically, I haven't thought about it. I don't know if Grover gets you anything. But it's more like if you're just hashing your password or using the symmetric key crypto. You first exchange a key with Diffie-Hellman, and then you switch to symmetric key crypto because it's faster. What is the exact security there? And you care about exact security because it affects parameter sizes. I mean, I think it leads to really interesting query complexity questions. But the reason you care in practice is because of efficiency. But
yeah.
Okay, so the question is, what happens? So we have our underlying assumption. We want to build crypto from it. Can we just take our classical security proof and just make it work quantumly, or do things break down? So let's run through one example. Let's talk about PRGs. So a PRG is just this function that expands the length of its input, and the output should be, so even though the output is big, relative to the number of possible outputs, it should look like a random output. Okay, and the question is, what if we want to increase the stretch of a PRG? So we have a PRG that increases by 1 bit, and now we want to increase by 2 bits. Well, classically, what do? You just chain them together. You feed your X in, to G, you take part of the output of G and you feed it in again, and now you suddenly have two bits extra of output. And classically, we can prove this is secure. I'm going to run through the proof. This will probably be very annoyingly slow, but because I assume everyone's familiar with this, but I just want to run through it just to have a complete example here. Okay, so how do we make the proof go? So suppose it's insecure. Suppose that G2 actually is not a pure G. What that means is there is a polynomial time adversary and a non-negligible epsilon, such that you're able to distinguish the outputs of G2 from random. Okay, and then we do a hybrid. The first hybrid, or hybrid 0, is where you're actually given G2. The second hybrid, we kind of chop off the top. We give this weird thing where this bit is random and this bit is just generated through G. And then finally, in hybrid 2, we give just random string to A. Now, if I define P0, 1, and 2 as a probability A outputs 1 in these experiments, the guarantee of our supposed adversary A is that P2 is far away from P0. Okay, so what does that mean? Well, there's two cases. So we don't know what P1 is, but we know one of two things holds. Either P1 is far from P0 or P1 is far from P2. That's just triangle inequality. If P1 and P0 are separate, we can actually turn A into an adversary B for G, as I've described there. And if P1 and P2 are far apart, we can get an adversary for G in a slightly different way. Basically, just using the fact that each adjacent hybrid differs by one application of G, we simulate the rest of the hybrid for ourselves and take that one application of G, and that's the part that we forward to the adversary. Okay, and so in either case, you get advantage epsilon over 2 against G, and by the assumption that G was secure, that's impossible. Okay, so that's how this is like the bread and butter of crypto proofs. So what happens when you move to quantum? Well, okay, I'm going to be talking about definitions later in the hour, but for now, let's just take it for granted that the way to upgrade the the security of a PRG to quantum is to just say that the adversary A is allowed a quantum compute. So, instead of PPT, we just say QPT for quantum, right? But otherwise, the definition stays the same. Well, actually, the same theorem works. So if the underlying G is a post-quantum PRG, composing it in this way gives you a secure G2. Why? Well, it's literally the same proof. Literally all I'm doing is replacing PPT with QPT and classical security against post-quantum security. Just, just find replace, and literally the same proof works. Okay, and the point is that the proof of security for G2 actually doesn't care how A works. It really doesn't matter. We in the classical crypto setting, we always imagined A being a classical polynomial time adversary, but it really could be anything. It could be quantum adversary. It could have, this is a picture of a closed time-like curve. This is some, sci-fi computational model that's even better than quantum. Or it could just be pure magic. We don't know. It could be anything. No matter how this box works that breaks the G2, the reduction will work to break G. And to put another way, the proof treats A as a black box. And I'll point out that people have actually cared about black box reductions for a long time, but from the perspective like understanding the limits of provable security. But here we're really taking advantage of that for like useful stuff, because we can actually say, hey, well, if the proof treated it as a black box, we're gonna have to be very careful about what we mean by a black box here. But the proof literally didn't care anything about the computational model of the adversary, and therefore, it works quantumly as well. Okay, so this might lead you to think that actually this always works, and you can just say, well, if I have a classical proof, pretty much all the classical proofs in crypto are you make black box use of the adversary, therefore it works quantumly. But I'm going to ruin your day and tell you that that's not the case. Due to lack of time, I'm going to skip one example. Okay. So the example I'm going to talk about is something called commitments. So a commitment is, I'm not going to really be that careful about the definition, but I'm going to imagine a computationally binding commitment. So we're going to ignore hiding. You also care about that. But it basically says that no efficient adversary can find, the commitment's this probabilistic process that takes a message in randomness and outputs a commitment. And the computational binding says that you can't find two message randomness pairs that map to the sync. Or really, I guess you only care about the messages being distinct, or whatever. Okay, so what do commitments allow you to do? Well, I'm going to describe a very simple coin tossing protocol, where it's like kind of the first thing you would think to try when you're trying to have Alice and Bob. They want to establish a random coin that neither of them can bias. And I'm not going to define a formal security model for coin tossing. Just describe this protocol and its properties. So what does Alice do? She commits to a random bit, sends it to Bob. Bob sends a random bit to Alice, and then Alice opens her commitment, and the final bit that they agree on is the XOR of the two. Or Bob outputs bot if the verification fails, if Alice cheats. So this is a little different than how we normally think of coin tossing, but forget it. Okay. So I want to prove that Alice can't bias B. I'm going to ignore Bob. I'm just proving that Alice can't bias B. So, well, let's do a proof. So suppose towards contradiction that Alice can bias. So she has a strategy where she sends a commitment, gets Bob's bit, and then she sends an opening, and the probability that the resulting bit B is 0 is greater than 1/2 plus epsilon. And so remember that if this opening is invalid, Bob outputs bot. So that's like there's 3 possibilities of the outcome, and we're saying this particular one has a probability greater than 1/2. And intuitively, what this says, if Alice is able to do this and actually exceed 1/2, it says that regardless of Bob's bit B, there's a good chance that that Alice will be able to open it to whatever she wants to. You know, she's targeting b equals 0, which means she wants her opening to match Bob's bit. And regardless of what Bob's bit is, there's a good chance that she will be able to do that. Okay, my animation got messed up. So let's prove that Alice can't bias the bit. And let's formalize this intuition. So step one is we're just gonna run Alice. And when we run Alice all the way through, we're gonna run it with Bob's bit being set to 0. And we're gonna get some opening here. All right? And now what we're gonna do is we're going to rewind the adversary because we're imagining A is classical and we can just have a program trace, right? So we can just go back to a previous line of execution, go back to after Alice sent C, and now we run it through with b equals 1. And we get another opening. And it's not hard to show that, well, these are basically just two runs of the protocol. Like each run of the protocol looks correct. They're correlated through C, but never mind. Each run of the protocol looks like an honest execution of the protocol. And with some analysis, you can show that the probability that Alice's bit in this case actually equals 0. Remember, she's trying to match her bit to Bob's bit. So the probability that she matches to 0 here, probability that she matches to 1 over here, and that both commitments are valid openings, that probability has to be polynomially related to epsilon. We can show this. We'll just take it as granted. Okay, and now this is a contradiction because look at what Alice achieved here. She opened her C to 2 different messages that violated the security of the commitment. Right? Okay, so that works, and we can prove the security of the coin tossing protocol in this model just based on the computational binding of the commitment. So what happens when we move to quantum? Well, first thing you would try to do to get a new security definition is you would just take the commitment security definition and you would just upgrade all of the PPTs to QPTs, right? So that's what I've done here. So it's the same game, but the adversary now is allowed a quantum compute. And we can similarly kind of consider the coin tossing goal. I'm not going to define it. Okay, so let's try to run through the classic proof. You know, let's see if it actually works. Okay, so we run Alice through once. This is okay. Nothing. We can always run the adversary once. That's fine. And now we try to rewind, but this just doesn't work. And remember, we had this observer effect where we said if you do a measurement at some point in your computation, you're actually going to affect later results. So I ran this, getting this is a classical string that I extracted from the adversary that required a measurement. And in the process of extracting that classical value, I actually altered the adversary state. And what that means is I can't rewind and go back. Or to put it another way, in the quantum world, there's no such thing as keeping a program trace because, right, keeping a program trace is effectively, you know, you can think, oh, maybe I copy my current state of the algorithm to another register, but we can't copy states, right? No cloning theorem. Or you say, oh, well, maybe I look at it and measure it and write it somewhere else. We can't do that because of the observer effect, right? So anything I try to do to get this out of here and then try to rewind to go back is going to be a problem.
So does this apply even if you have a non-black box access to the adversary?
Yes. Yeah. It's just about, it doesn't matter. You can have the full circuit. It doesn't matter. The fact that you're extracting this thing here, that's a measurement. And the observer effect means that you just messed up your state. So you can't backtrack and go backwards because it's, you changed it. So when you try to reverse things, you're going to get something else. And there's no guarantee that you got anything useful.
Is the hiding property in the opposite direction, that one still holds?
Yeah, the hiding, so hiding would come into play when you're trying to prove that Bob can't bias the bit, and that's fine. There's no issues there because the proof of that is just going to be kind of a straight line proof, just like the PRG case. So that's fine. Okay, and it gets worse. We can actually show that there is in fact a problem. So this was first shown by Embanus, Rosmanis, and Unruh. Unruh clarified it, and I'll just briefly mention our result at the end. just talking about this theorem. So basically what they showed is that you can actually have a commitment that is binding in the post-quantum sense. So replace PPT with UPT. But Alice has a near perfect strategy, even with that commitment. So even though, you know, Alice like commits to the C, somehow she's able to, you know, answer with 0 or 1, depending on whatever Bob's bit is, but she can't produce both.
So is there any setting where rewinding works?
Yeah, we'll talk about that. Yeah, and so what the Mbanus and Nunru and Rosmanis showed is they showed this relative to an oracle, and then I'll just shamelessly self-promote, and Omri and we just showed a construction that does the same thing in the standard model. And there's other cool stuff with our result, but that's one consequence.
Is this a security claim or an attack? Is Alice
So it's a theorem that says there exists, you know, either relative to an oracle or relative to suitable assumption, there exists a commitment that is binding in the post-quantum sense, in the sense that I defined,
Okay, so
QPTs, but there is also an attack on that commitment where the commitment is still secure, but Alice is somehow able to break the coin tossing protocol.
So basically, you're saying it's the wrong definition in the post-quantum sense.
Commitment is good, coin tossing bad.
Oh, okay.
Well, I mean, my take is that the definition of commitments is wrong in the quantum setting, right? And then the key point here is that the ability to produce either of two values, so either Alice produced 0 or 1, she can do either one. She can do either one, but she can't do both at the same time. Once she produces 0, I'll bet, you know, she's done. She can't produce 1, because that would break the post-quantum binding of the commitment. But she can, if she doesn't produce 0, she can choose whether to produce 0 or 1. Okay, and then, so yeah, so some takeaways from the discussion of the reductions. So basically, if your reduction treats A as a black box, just runs it once, there's no rewinding, no interaction, probably your reduction works in the quantum setting. I don't think we have like a fully formal theorem that states this, but just intuition, your reduction probably works. But you have to be careful. I ended up skipping the idealized model stuff because I don't think I'll have time. Maybe I'll come back to it at the end. But basically, if you're going to do a proof in the random oracle model, you have to throw this away.
Single line. So you don't use rewind.
Yeah, if you don't use rewinding, because you're just doing a single run. So, you know, rewinding we just said is bad. Single run, black box, though, seems okay. Like if basically all you're doing is literally just a hybrid argument, things should work. But if you're rewinding A, you have to be careful. If you're using random oracles, we didn't talk about random oracles, but if you're using random oracles, you have to be careful.
So there was a paper which was trying to formalize this with YAL, wasn't it your paper?
Yeah,
Post-quantum black box reductions.
there is a notion. So open questions from this space. You know, I don't know that you know, there's been some exploration of which proof techniques work, which fail, but I don't think we have a complete understanding here. There was definitely some progress towards kind of a general result of the form that I just described, but again, I don't think it's complete. Okay, again, we skipped random oracle stuff, so maybe I won't mention that. And then we're going to talk about rewinding momentarily, but we have some specific techniques for rewinding, but it turns out that they're going to all require additional conditions, either a stronger security assumption or some assumption about the protocol, and just kind of understanding like what are the conditions we need for rewinding.
Rewinding is a problem also in the classical setting with universal composability.
Mm-hmm.
Is there any kind of connection between composability and the quantum?
Aside from the fact that people have considered UC in the quantum setting, I don't know that like those issues necessarily relate to this issue. They might. I'm just not sure.
So we had some paper in 2022 where we just found something called universal reductions, which was like kind of like the UC analog of reductions. And so it's a reduction that would hold even in the presence of some outside environment. And I think we had like a formalization of that previous thing, but maybe it's missing something. I don't check.
Okay, yeah, I'm not sure. Yeah,
But yeah, that result was actually very simple. So is there a reason why you think it's like the previous
I mean, things get so again, like if all you're doing is a hybrid argument, you're fine, right? And You could probably define a class that captures hybrid arguments and you're fine. But like, I know one, I don't remember everything that went into here, maybe y'all can comment, but one of the issues here was like, what if you have quantum auxiliary input? That's gonna really change things. And that might come up in certain cases. And depends on your model and exactly what you're trying to do. But yeah, we don't have a theorem that basically says if your proof is of this, then it's good. If your proof is like this, then it's bad. That's we're probably not going to get something quite so good. But
our thing doesn't definitely not an if and only if.
Yeah.
It was an if and only if
Sure.
or abstract model.
Yeah, but we want to get bigger, and we want to approach the bad set of reductions as close as we can. And I don't think we've gotten there yet. Okay, so that'll lead me into post-quantum definitions. So, this is going to be motivated mostly by this commitment example. So we saw that commitments, the obvious way you would define them fail. Or it fail in the sense that it's a sensible definition and it makes sense, but then it doesn't give you all the results you would want. So what do? And the answer is we come up with something better. We come up with a new definition of commitments that really takes advantage or takes into account how you would actually want to use it. So the notion that everyone has kind of converged on as the right notion of a commitment is something called collapsing. So a collapsing commitment is defined by the following security experiment. So this is an inherently quantum experiment now. Okay, so what does A do? A is going to send over a superposition of openings, superposition of message randomness pairs. And the challenger is going to compute the commitment corresponding to that opening. And then do one of two things. Either they're going to just, either they'll measure everything. Maybe I should have put a C here, but because MNR defines C, measuring MNR is the same as measuring everything. So either they compute the commitment, then just measure the whole state, and they get MR commitment, or they just measure the commitment and nothing else. Okay, and now the state collapses. So in this case, the state is just going to be this like singleton state that just has, it's a quantum state. We're thinking of it as a quantum state, but it's really just 1M, 1R, 1C. And this thing is going to have 1C, but it might be a superposition over M's and R's if it's if the commitment's not one-to-one. Okay, so the challenger does this. This is all on the challenger side, and then they send that state back. So either this MRC classical or the superposition over M and R. And Alice has to tell which is the case.
So are you trying to capture binding or hiding?
This is for binding. So hiding is the same as before. Hiding is literally just the same indistinguishability thing. But for binding, we will need the stronger notion. And I might go back and forth in language between talking about commitments and talking about hash functions. There's basically an identical game for upgrading collision resistance of hash functions to a collapsing hash function, and collapsing hash functions give collapsing commitments. So they're very similar, and I might kind of go back and forth.
That's cute. I mean, I understand that this definition works and makes sense, so
Yeah.
we use it. But one can also think of defining a definition that's not inherently quantum like this, which is instead of requiring to open two, which is not sufficient, you can add something like, okay, the challenger will kind of choose one, open or random.
Basically, you win the coin tossing game.
Basically.
Yeah.
Right?
So you can define it that this is something called sum binding. So prior to Unruh's work, there had actually been a few attempts at defining commitments, and the problem is that, okay, fine, if your one application is the coin tossing game, then the sum binding notion actually directly, just assuming it. But if you're trying to do more sophisticated things, then you have to come up with more sophisticated assumptions. And it just became kind of a mess, and it wasn't clear that you were really capturing everything. Whereas this just works. for pretty much everything.
No, because the reason I'm asking is one can think of the following. Look, today the algorithms are classical. Tomorrow they're going to be quantum, and maybe 2 days from now they're going to be whatever. So ideally, you want the definition, especially if you're talking about black box, not to really depend on the model of computation. And so the original definition definitely depends on the model of computation. This definition also depends on model computation. So there's something to be said about having a definition that is.
Yeah, I agree. It is a little unsatisfying. I don't know what else to do though. You can come up with these like kind of game-based definitions where, you model the coin tossing game, or you try to model kind of richer protocols. But I don't think that there was ever like kind of a one definition that caught
Yeah,
everything.
basically saying we don't have a good definition that's independent of the model.
And
I think that,
okay.
like Nick Splitter and like the Universal one, they have a paper showing that sum binding, the definition you're talking about, is equivalent to
Yes.
collapsing.
I see.
So it's like maybe you use this one when you do certain kind of security proofs, and maybe if you want something that's like computational model agnostic, you can use sum binding. But I agree with you. Like, I feel like you should have a definition that captures the fact that like a physical safe where you write like number on a sheet of paper and put it in like is a commitment. And it's a little unsatisfying that collapsing doesn't like is not
But
satisfying.
you're saying if that's equivalent, then this is just easy to work with.
Yes.
That's maybe
Yeah.
the
Yes.
correct kind of.
Yeah, so the way I think about it is that there's kind of two goals with crypto assumptions, right? So one is you want to capture what are actual like real world attacks and do so in a conservative way. And the other one is you want a definition that's easy to work with and easy to prove things with.
Exactly.
Sometimes they're the same, right? CPA security, right? Really easy. Sometimes they're not the same. And I think this is an example where I would love if there was a definition that kind of simultaneously captured both, but right now we don't know. And this is the kind of the latter one.
Yeah.
Yes.
What's the justification for measuring R as well as M? Like, classically, it's okay to have multiple randomnesses that you could for your commitment, as long as you can only open
Yeah.
the same message.
I think actually in the original paper you might have only measured M, but there's this like strong like for the commitment binding, right? You could also say like, yeah, you only have to have a different message, or you can say actually all you need is a different message randomness pair. And it's kind of the same analog. So there's like a weak and strong form of binding for classical security commitments, and we have the same thing here. This is what you get from collapsing hash functions, and I was kind of thinking about collapsing hash functions when I wrote this. Yes.
So is it true, not to complain about the definition, but is it true that if you are in a classical world, assume that quantum is wrong, so everything is classical, then this definition is trivial, is satisfied by any protocol, because what I can do, there are no superposition, can only send a single MNR. And on the other side, there is only one corresponding commitment, observing makes no difference.
Yeah.
And
Sure.
okay, so in this sense, it is unsatisfying that.
Yeah, I guess measurement doesn't really do anything classically, right? So it wouldn't be interesting in a fully classical.
It would be satisfied by anything, even
Yes.
something that is not binding
Yes.
at all. It's not a stronger definition unless you have.
Yes. Now in the quantum setting, so I didn't write this on the slide. So in the quantum setting, this does imply collision resistance of the commitment.
Yeah.
That's probably not obvious, but basically, if you could find a collision, you just send over the superposition of both of them. This case makes it fully classical. This case leaves it untouched, and then you can distinguish the two cases because you can actually tell whether you're in the superposition or not. So yeah, but that requires actually sending a quantum state here. If you're sending a classical state here, then you can never win.
On the other hand, if you have a commitment scheme which is computationally hiding and statistically binding, then it will automatically satisfy this.
Well, classically, everything's satisfied.
It is statistically binding classically, then
Yes. Yeah. So
you get the same distribution. They are identical.
Yeah. So even quantumly, like if you have a classical commitment where you're in the quantum setting, statistical binding implies this. Absolutely. Yeah, and this was actually kind of like, this was only formalized in 2016, but earlier attempts to get around this rewinding problem had basically like moved to the statistical binding setting where you kind of get this for free. They didn't talk about it that way, but yeah, and so actually, that leads me to my next slide. You're being a great plant. So the intuition for where this came from is suppose that the commitment is actually injective. Then measuring the input and output, it's the same effect. Measuring the output information theoretically determines the input, and measuring the input information theoretically determines the output. So, so you actually get perfect collapse, or maybe statistic. Oh yeah, injective you get perfect collapse binding, and if you had like statistically binding commitments, you would get a statistical collapse binding. And basically, so what is collapsing or collapse binding? It's basically like a formalization of this particular property that statistically secure commitments give you, but it still works even if you're not statistically binding. And okay, and so let's actually see how you use collapsing to fix the rewinding issue. I'm not going to go through the full proof, but I'll just give some like kind of hand wavy arguments here. So the first thing we're going to do is we're going to remove all the measurements from A that happen after they send the commitment. You're just going to have to take it as granted that you can do this. It's an easy exercise. Basically, what you do is anytime you were going to measure, you instead just like, if you're going to measure X, you just like write X comma X, and you just take the second X and you just move it somewhere else and you never touch it again. And this this A prime will behave exactly to A. So we can remove all of the measurements from A. And now the point is, imagine we remove, so okay, so we measure here to get C, but after C, we don't do any more measurements. Now we actually can rewind. Why? Well, remember that there's no measurements in A prime. So all A prime is now is a unitary, and unitaries are automatically reversible. So we can rewind A prime back to C, and then run them again. Okay, but we're not done. We're far from done, because when we ran A prime to get the state, but then we rewound. So we actually erased the state in the process of rewinding. Applying the unitary backwards just completely erased everything A prime did leading up to this point, including this value here. So even though so basically right now, step 1 and 2, they just cancel each other out. We don't get anything useful out of it. And we only get, this opening to 1. Okay, so we can we'll get there. So Unruh, another paper by Unruh, showed that I think I got the right one. So that, well, okay, what if I measure if this one is valid? I'm not actually going to measure this whole thing. I'm just going to measure one bit, which is whether this is an opening of C to 0. Right? And I'm going to do the same thing over here. So this one, we know each one kind of individually. Like if I just did this measurement, we know that he's going to open correctly with probability ½ plus epsilon.
So to measure that this is an opening C to 0.
Okay, yeah, I didn't write it out, but basically, like, I will, imagine the classical computation that says, is BA 0 equal to 0, and is this a valid opening of C? I'll run that classical computation in superposition, write the bit of the output to a new register, and just measure that. Right, so I'm just measuring this one bit, leaving everything else quantum.
Whose value is a single bit, and then we measure the result that comes.
Yes, right. So I'm not measuring this whole thing here, so I don't have a classical string yet.
That's a trick you can do.
You have to be very careful. I mean, classically you can do this, right? Or classically you can always look here. Quantumly you have to be very careful because remember, doing any measurement here changes things. So if I didn't do the measurement, I know that this outputted, a valid thing with probability ½ plus epsilon. I know if I do the measurement here, this outputs the right thing with probability ½ plus epsilon. But if I do both, a priori I don't have anything. However, it turns out that if you're only measuring one bit, you kind of didn't change your state too much. I'm not going to prove this. It's it's just some math, but you're just going to have to take my word for it. But it turns out like measuring one bit doesn't erase very much of the state because it's just one bit, right? So half of the state is still there. And so it turns out that you can show not only does it not change the state too much, I mean, you can still change it kind of significantly. You can because you're erasing half of it, but you're keeping enough of it around that you will actually, classically you get an epsilon squared here, and you can get an epsilon cubed quantum. So measuring this one bit here didn't mess things up so badly that I get nothing here. I still get something, somewhat useful, though I went from epsilon squared to epsilon cubed.
this lemma, it's that kind of generic. So if I have a quantum task and I'm a quantum algorithm and I succeed in just forget about commitment and I succeed probability epsilon, and then you run me with some challenge and you just measure if I'm accepted, and you get, and then
you rewind.
again, it's always that's kind of a generic.
Yeah, yeah. No, I'm lying and cheating a little bit here because you need an addition. The actual lemma says that if this is a random challenge and this is a random independent challenge, you get epsilon.
Okay,
But you need to make sure they're different. So there's a little more. There's a better lemma that actually captures what you want.
But taking it as a constructive thing rather than an proof, I can write a circuit whose effect is to erase certain information.
If you knew what the information was, yeah.
Like what I want, yeah. You have to-
Right. So I'm reversing this, but I can only reverse it because I knew how to get there in the first place. Right. I constructed the state, and then I'm doing the exact opposite of what I just did to construct the state. If you gave me a kind of an arbitrary state and I didn't know how to construct it, then I wouldn't be able to kind of deconstruct it either.
Is it bad? Is the epsilon cube bad?
I mean, in practice, you might care. For theory, we don't care so much. There is a question of what happens if you need to rewind multiple times. And this is true classically too. Like if you do the naive thing classically, this exponent goes up with the number of times you rewind. That happens quantumly too. And you have to do like kind of more sophisticated rewind. Like classically, you just run this guy multiple times to kind of amplify your success probability. Quantumly, you have to work harder. But for the most part in theory, I don't think the squared versus cubed makes much of a difference.
Do you know an example with epsilon squared at least or something?
Oh, like a.
What's the best attack? What's the best?
I think this is optimal in the fully generic setting. If you just imagine running a process, measuring a bit, rewinding, running again, I think this is optimal. Obviously, certain processes, like if your A is classical, then you would get epsilon squared. Okay, so we're still not done. All we've measured is whether this is valid, but we're still rewinding. We're still erasing this whole register when we do the rewinding in step 2. Okay, so what do we do? Well, first thing, I can measure this guy for free, basically, right? If this is valid, I have this state here, and I know that it satisfies the predicate I'm applying here. And so if this is valid, I measure this, and I'll actually get my opening of 1. And now what I want to do is I want to additionally measure this and get my opening of 0. And I know if I measure this here, I actually will get an opening of 0, assuming I was valid. The problem is that measuring this thing potentially destroyed this. I know, might have just completely destroyed this. My guarantee on being valid was only when I measured just the valid bit. When I measured the whole thing, who knows what happens? And the counterexamples by from before show that actually there are protocols where even though measuring valid is fine, measuring this will destroy the state. But this just becomes straightforward reduction to collapsing, right? Because if measuring this caused a noticeable change in the probability of a collision, well, that's a distinguishing attack on whether I measured this or did not. And like measuring I've already measured C, right? And so this like exactly fits into the collapsing security of the commitment. So if the commitment is collapsing, actually this does work, and I can measure that out.
I think there is something very unsatisfying. So, what you would expect is that you fix the definition and there is a 2-line proof. And you're saying now the argument is like super counterintuitive. First you do some weird thing with 1 bit, and you go from epsilon to epsilon cube. Then I don't know, is it like the way you expected? To me it says that
I mean, it's not much harder once you have this Unruh's lemma, right? This might have been a page proof. It wasn't incredibly deep or incredibly complex, but not obvious a priori. And once you have this, it's still a relatively straightforward proof. You just need to kind of like make sure you're doing the steps in the right order. And this is all because of this measurement principle that just, I think the answer is like in the quantum setting, our lives are just harder. But it's still pretty simple. It's just a few hybrids. It's more than you would have classically, but it's just a few hybrids. And ultimately, the actual algorithm, the actual reduction is actually the same as classical, It's just that to analyze it, you have to do a couple more steps in the hybrid.
That's not cube, I assume there is a more. It's a page.
No, it's literally, I mean, literally what I'm doing is I'm measuring this. That kind of implies measuring valid, because I can determine valid from this. Rewind, measure this, and I'm done. So it's literally the same proof you would expect. With the analysis, we have to kind of go through these extra steps. And it's just it's because of this measurement principle or observer effect that, we have to be careful with doing measurements here. And, so we have to kind of break things up into more hybrids in order to show that we can do that. And then there's this information theoretic Unruh's lemma that we need to employ that you don't have classically.
It's a bit of an annoying question, but you said that in Unruh's paper, the original definition is like not involve measuring R.
I think so.
It's like a little weird to measure R because it's kind of saying that you're also committed to the randomness, which is why we do that. You can imagine taking a commitment and like tacking on like a dummy bit R that where you could detect it, but it doesn't break the commitment.
Yeah.
It's a little weird that this proof requires like measuring R, right? But like you don't seem to get a contradiction if you only measure B.
Yeah, that's a good point. I hadn't. I feel like this came up in some paper. It's been so long since I've thought about it. But the definition I wrote is the one that gets you what you want. So it's the one you get from hash functions anyway. So
yeah,
you might as well just use the stronger one.
Yeah.
But yeah, that's a good point. I don't know if the weak one works. Certainly not with this proof.
Right.
And the constructions of these collapsing hash functions, like, are they known from good assumptions?
Next slide. You had a question?
Why is measuring D not enough?
So if you, right, I'm trying to violate the security of the underlying commitment. So I need two message opening pairs. If I don't measure R0 here, I only have the message, I won't have the opening.
So you just need enough to decommit. You don't necessarily need all the randomness, but
well, to violate the underlying binding of the commitment, I need the whole opening, so the whole random.
R0 is like the opening. It doesn't have to be the actual randomness. It's like an opening.
Yeah, fine.
It stands for.
Okay. Yeah, so in terms of constructions, we're in good shape, I think. So first, as we already said, any injective commitment is automatically collapsing. A random oracle, Unu showed that's collapsing. Lossy functions, which you can build from lattices, these are collapsing. Basically, you have a hybrid where you're injective on some part, so you can kind of imagine why lossy functions would work here. We show that the sys hash function is collapsing. So, like in terms of feasibility, this is redundant, but it shows that there's multiple ways of getting these constructions. And then we also showed from a handful of other assumptions as well.
The question is, can you get it shrinking, right? Because these are not shrinking. Like the lossy.
Well, you compose the lossy function with pairwise independence. Okay, just like lossy functions apply collision resistance. It gives you this too. Yeah.
So if you use injective commitments, then the proof becomes much simpler, right? You don't.
Yeah, injectivity makes things a lot easier. But oftentimes you care about succinctness, like if you're doing succinct arguments or something like that. Yeah, and so and this is not a formal theorem, but more or less from the perspective of a feasibility result, if you have any post-quantum, more or less any post-quantum assumption we have that gives collision resistance, we can also use that assumption to build collapsing. Now the construction may be different. There might be like way worse in terms of parameters or something like that, but very, very loosely, that's the status that we're in. But we don't know a generic conversion between collision resistance and collapsing. And yeah, as I mentioned before, we do have some better rewinding techniques too that handle multiple rewinds or give you better guarantees about the rewinding. Yeah. Oh, just so that like in this work here, we considered the case where you have to rewind a bunch of times. Like if you're doing Killian succinct arguments, you need to rewind a bunch of times. What happens there? Unu rewinding doesn't work because that exponent just grows with every rewind. And classically, you can just kind of amplify your success probability by doing many trials. But quantumly, every trial messes you up, or potentially messes you up. So we had to develop a new rewinding technique, and then some follow-up works made it better, gave even stronger guarantees. Okay, and I want to just point out that the collapsing is not always necessary. It really depends on your application, and sometimes plain old collision resistance is just fine. And for example, imagine you have a signature scheme, and for whatever reason, for efficiency reasons, maybe you're going to hash your message before you sign it. Well, as long as you're not getting into some new model where you're allowed superposition signature queries, as long as you're kind of in the same model where you're just allowed classical signature queries, here collision resistance is actually just fine. If you run through the classical security proof, based on the existential and forgeability security of the signature and the collision resistance of the hash, everything just works, and you prove the security of the new signature scheme. So yeah, basically like collapsing, it comes up in the context of rewinding. I'm not sure if there's any other regime where it's necessary, but sometimes you don't need it. And let me skip the last part and just move to some just a few open questions. So I didn't get time to talk about these fully quantum notions where now you actually you have a PRF and you're allowed superposition queries to the PRF, or you have a signature scheme and you're allowed superposition queries to the signature scheme. So there's this whole superposition attack security that you can consider. Maybe you argue it's contrived, I don't know. Some of these notions have been very useful in actually building quantum protocols. So I think it's well motivated. But there's a lot of open questions here. So for example, we know how to do PRPs against superposition queries, but they're rather inefficient. We don't know how to prove Ruby-Rakoff is secure. I won't talk about indifferentiability. And also this model, superposition queries to signature schemes, we might have the right definition. Again, I think this comes down to this question of best for use in security proofs versus what actually captures real attacks. This is good for security proofs, not great for attacks, I think. I don't know, I think the status is open here. Yeah, and with that, I will finish.
Questions?
Can we go back to the original definition? I didn't understand why
Of
psi prime, when the state gets sent back to Alice, the original, I think it's the original.
This one? The collapsing.
How are there any special constraints to make sure that psi prime can be sent back, that it's physically plausible?
We just imagine, I mean, it is a well-defined quantum state, and we're just imagining that we can just send it back.
Send it back.
Yeah, so yeah, Alice's interaction here is fully quantum. He's sending quantum states, getting quantum states. Yeah, I mean, I guess I'm not sure I exactly understood the question, but yeah, from a modeling perspective, there's no issues just sending the quantum state back to Alice.
Okay.
Any other questions?
Yeah, this is something, but I think this is my elementary understanding.